So let's talk about what happens when you do addition across this double bond. And I want to focus on this because it's going to kind of also explain another effect we see with these types of complexes. So we always go through the aldol addition product first, and we can subsequently get elimination to give us to the unsaturated, the alpha beta unsaturated complex. Now, first of all, that alpha beta unsaturated, what is that referring to? Well, if we look at our ketone, we have an alpha carbon adjacent to it, and then we have a beta. So when we say alpha beta unsaturated ketones, what we're saying is that there's an alpha carbon, and next to that's a beta carbon that contains a double bond. Now, when we do this, we initially go through this alcohol intermediate. When we do the elimination, we always end up putting the double bond between the alpha and beta carbons. We don't go anywhere else. And the question to you is why? Why would we not, if we have elimination reactions going on, not go to the more, why not eliminate, using Zaitse's rule, eliminate the more from the more saturated carbon? And the reason being is that when we do the elimination between these two, we create a conjugated pi system. Because these double bonds are in contact with each other, they end up forming what look like dienes because of the double bonds, and they're much more stable. But because these pi systems are interacting, we also end up changing how the chemistry of addition reactions go. So I've got HX here. My question to you is, where would you add? Well, if it were just an alkene, meaning that we don't have this ketone group adjacent to the double bond, we would expect the X, the halogen or whatever nucleophile we're adding, to go to the more substituted carbon, because the more substituted carbon here is going to carry the positive charge because it's more able to stabilize a carbocation. This may not be the case with alpha beta unsaturated ketones. The reason being is that if we were to draw a resonance structure, so the reason why we justify why alkenes add the nucleophile to the more substituted carbon is that if we draw a resonance structure and we pull that double bond to a lone pair, the lone pair, we're going to have a lone pair, we're going to have a carbocation. The carbocation is more stable on the unsaturated carbon. In this case, if we remove this double bond and we resonate, it's going to be more stable here to put the two electrons on the alpha carbon and not the beta. The reason being is that this will allow us to undergo tautomerization to form an enolate or an enol. So because putting a lone pair here becomes more stable because of the resonance with the carbonyl oxygen, this alpha carbon ends up actually taking a more negative charge. This is going to be the nucleophile. So we're going to get H addition to the alpha here, and the beta is going to get the addition, even though in this case the beta is the less substituted carbon. So keep this in mind when you do addition reactions to alkenes that are adjacent to ketones. Unlike alkenes just by themselves, we're not going to follow Zaitse's rule. We're going to have to make a judgment call, and this judgment call is going to put the hydrogen addition, if there is one on this addition, on the alpha carbon, and it's going to put the nucleophile addition onto the beta carbon, regardless of what their degrees of substitution are.